We start with a new topic which is called optimization techniques in large language model, specially focus on the attention or the self attention mechanism using KV caching for next token prediction. So before going to this topic, let's kind of see what will be the scenario for the self attention. So we generally know from the previous uh, lecture, right, what is self attention, where attention mechanism is defined by query key and value given by shortcuts of query, that is q into what product of k transpose divided by d model into v. Okay, now let's assume query is given by 4 tokens. So token 1, so this is the query token, token 1, token 2, token 3 and token 4, which is having a 4 cos 512 dimension. So 4 is nothing but the sequence of the token, so which is actually total 4, and 512 is the embedding model, which we earlier lecture considered as a D model. Okay, now do the multiplications with the KT. So K transpose, where K token, so this is the token number 1 for key, so this is the token number 2 for key, this is 3 and 4. So what is the dimension? So this dimension is 512 cross 4. Now what will give? It will provide a kind of a 4 cross 4 matrix of Q K transpose. Now we again do a multiplication with respect to the V. So obviously we will do a kind of a softmax on the top of these, correct, and multiply with the V, which having a token 1 2 3 4. So the dimension is 4 into 512. So finally what is inner matrix? 4 and 4 will get cancelled, so final dimension is 4 cos 15, sorry 512, which you provide a attention mechanism 1 2 3 4. Clear? Now let's come to the inference. So it's very much interesting. Now in the inference part, let's the first inference, or the first step inference, is that t is equal to 1. So we take the first token of q, which is nothing but 1 cross 512 dimension of this token 1. We do the multiplications from kt, which dimension is 512 cross 1. So it provides a kind of a key transpose. On the top of that we will do softmax, which the dimension is 1 cross 1. Now we again multiplied with v. So this is what? It is 1 cross 1 matrix. So we will just multiply with token 1. So what is the dimension it will come? So 1 1 cancel as a inner matrix. So final attention come, right, is a 1 cross 112. Sorry, wow, 512. Vector I can say. Okay. Now in the inference 2, what is the scenario? So in the inference 2, we takes the 2 tokens, because it's the second inference. Now we do the tokens, again KT, which is also a kind of a 2 tokens out of this KT. So these are the token for key, so these are the tokens for query. Okay, we do the multiplication, so it becomes a 2 cross 2. So earlier it was 1 cross 1 matrix, here it is coming 2 cross 2. Okay, now we multiply it with the V. So with the token 1 and 2, so it is 2 cross 512 matrix. So inner matrix 2 to cancel, so it will become 2 cross 502. So here if you see the attention mechanism, right, so the dimensions are actually increasing. So this one row, this is second row. Okay, so here it is token 1, it is also increasing here. Now if you see this, whatever this elements, so this is actually kind of a repetitive. Okay, so we'll see, like discuss in further steps. Now let's get the scenario for the inference 3. So inference 3 means 3 tokens. So 3 into 512 cross token for KT. We also have for KT keys tokens are 1, 2, 3. So inner matrix 5 cross 512 cancel, so we get a 3 cross 3 matrix. Okay. So again we compute or do the multiplication using the B, right? That is the value which also have a token 3, right? So if we multiply it, inner dimension for this 3 cancelled out, so finally it becomes 3 cross 3. So again if you see the attention mechanism, so the attention are increasing irrespective of rows. So here 3, 2, earlier it was 1, correct? So 3, 2, earlier in inference 1 it is 1. So again, so this part is a repetitive. Clear? Now let's come to the final inference, which is at t is equal to 4. So obviously we have 4 tokens and 4 tokens of KT, that is key. So here the matrix become 4 cross 4. Again we multiply with the V 4 comma 502. So final attention dimension is 4 cross 512. Now what is the interesting point to watch here? So the interesting point, if you see, let's concentrate on the T4. First part is that we already computed the dot product in step number 3, 2 and 1. Hence, can we cache it? So basically this value, red, whatever the red line I have put, these are already computed. So obviously we can cache it because these are pre-computed. We need not to recompute it again. Now what is this backend size, right? This part, let's concentrate on this part. Okay. Now in this part, we want to predict the next. We already predicted previous token, right? So the target is that we need to predict the next, but we already predicted the previous token 1, 2, 3. Okay. So in this case, right? So what is the interpretation? So generally for this case, okay. So this interpretation says, since the model is causal, right? We need not to consider the future tokens, but consider the past tokens. So basically this part, right, we are considering that if the model is causal, right, we need not to find the future tokens. So this is actually the future tokens, right? This part and this part. Correct? In that case, the past tokens or past historical tokens are sufficient, which we already cached it. Okay. Now, irrespective of this, right, if it is already cached, this token 1, 2, 3, we want to predict the next, we already predict previous token. So, generally, in this case, if we already have a historical predicted data, we can cache it, right? And the last token we can actually predict. Correct? So this is the meaning of this. So generally, if you see, so this is the logic for the KB caching. Because irrespective of these two values, right, this part we can cache it, and these 1, 2, 3 tokens are actually not required. We can actually focus on the present token, correct, or predicted token, next predicted token. Okay. Now what next? Now let's go to these next extension of this. So this is interesting, which actually finalize your concept for the caching. So earlier inference time, right? We already have a token 1, so dimension is 1 cross 512. So this token for key value is also 1, so it's 512 cross 1. So it's a 1 cross 1 matrix. So first token we pass for value, right? So we get a attention 1. Second interesting point right here. So earlier what we are doing, if the inference is 2, every time we are passing 2 tokens also. But here not required, because we are actually consider the presence token, correct? So for the token 2, right, we have a key, right? We already have a key 2, right? So these k tokens are increasing, but these q tokens are not increasing, right? So in this case, what is the dimension? 1 cross 2. Okay, again, if we actually multiply it by v, so generally 2 inner dot product get cancelled, so it finally gives a 1 cross 512. So what is interesting here? So interesting here is, if you see in the earlier part, for inference 1 to 2, the attention are increasing, correct? So attention 1, attention 2, right? For 2 attentions we computed for inference 2. But after final caching, right, we only focus on the predicted or the present token, which is actually casual. So inference 1 we have 1, for 2 also we only get a 2. So that is the interesting part here. And if you see, right, so this vectors is actually increasing irrespective of the rows, not in terms of a kind of matrix here. Okay, so it's actually increasing. So 1 cross 1, 2 cross 2, here 3 cross 3, here 4 cross 4. What here is what? 1 cross 1, 1 cross 2. Next in the third inference, what? Right? We have third token. So this is, KT. This is Q. So this is Q transpose T. So it's actually in a kind of increasing in terms of a row. So this is P. We have attention 3 only. So these attention are not increasing row wise. And finally, inference 4, if we see, so token 4 we have passed. So is the dimension 1 cross 15, 512, multiplied with the tokens 1 to 2, 1 to 4 for key. So what is the vector for Q K transpose is actually 1 cross 4, which we again multiply by 4 cross 512 tokens for V. So finally, what is the dimension? It is 1 and 512. So finally, what is the interpretation here? After caching, right? So all the attention output are 1 cross 512, 3, 4 for 4 attention, correct? But during the attention mechanism, right, we see, right, how it is actually cascaded, where the output of each attentions are actually increasing, right? Okay, so see how it is actually increasing till attention 4. Another interesting point is to note that, as I mentioned, the Q cross K transpose, right, is increasing irrespective of the number of dimensions. So it is 1 cross 1, it is 2 cross 2, for third inference it is 3 cross 3, and for the fourth inference it is 4 cross 4. But if I do the KV caching, right, is basically the dimension is in increasing irrespective of the rows only, not in terms of matrix. 1 cross 1, 1 cross 2, 1 cross 3, and 1 cross 4. So that means we can optimize the attention mechanism using the KVS caching. So what is the final interpretation we can make from this? So without KB caching and with KB caching. Okay. With KB caching, for every generated tokens, the model recomputes KV characters for all AVS tokens we have seen. So complexity per step is actually O to the power n, where A is the sequence length. So we also proved this one, sequence length. Next is that very slow for long sequences. So that is some of the disadvantage. So with KBS caching, what we see, when you produce token T, you compute K and V once and store them in a cache. So we already have shown this one. For next tokens, you only compute K and V for the new tokens. So basically, if we see for new tokens, we are actually computing, right? So these are all new tokens for each time inference, right? New tokens. Clear? So benefit: removes repeated computation for previous tokens, reduces per attention cost from O n squared to O to n. So this is a massive improvement irrespective of the complexity, and massive speed up for the long sequence. So let's say for a kind of example here. Okay, so this example is taken from this reference, right? Hugging Face Meta LLM Llama, sorry, inference KB caching, and the VLM page attention, right? KB caching speed up benchmark 8K. Okay. So assume that the model is 7E to 13B. Typically for the Llama and GPT architecture, GPU we have considered A100 or H100 class. So decoding is a simple sampling method. Batch process, we use one single sequence. Full attention recompute. Baseline, no KB caching we have considered. So for baseline, so that is that, state of the art. No KB caching. With respect to the KB caching, we are comparing for different token size. So initially we take 64 tokens. So it's for that, without KB caching, it is actually 180 microsecond. But for KB caching, it is coming 90. So this is basically a drastic improvement here. So for, if you see the timings, right, latency, right? So there is a improvement in the latency. So this is one of the greatest advantage. Speed up is also increasing irrespective of multiplication of 2, 2.9, 4, 7 up to 4, 2.3 irrespective of 8,000 tokens, right? So these are the percentage of the faster process. So these are the values for the speed up. So we are able to compare to provide a example to differentiate the advantage of KB caching compared to the attention mechanism or with no KB caching. So this is nothing but a attention mechanism compared to the KB caching, because in attention mechanism we generally use the QK transpose, the direct formula, sort max D model into P, right? KB caching we have shown how we can compute it. Okay, thanks for watching this video. So please provide a big like for this video. Thank you.